Okay, last time we assigned two homework problems, number 6 and number 8. So today I'm going to work on these two homework with you, okay? And this homework will be important because some of the homework, similar homework, similar problem, or kind of variation of this kind of problem will appear in the final, okay? Now let's look at the homework number 6. So in number 6, basically I have a function is differentiable, and the f prime is bounded. Okay, so from this assumption, we want to show that f is uniformly continuous. So this is a problem which connecting the differentiability to the uniform continuity. Okay, now the proof is very simple because this is a follow from the mean value theorem, and we talked about mean value theorem last time, right? Now, since f is bounded, so we may assume that there is an m such that the absolute value of the derivative is always less or equal than m for all x. Okay, so this is the assumption we can have, right? It's follow a direct consequence of the assumption that the f prime is bounded. Okay, and now we're going to apply the mean value theorem. Okay, now by the mean value theorem, you can see that there is so given x1, x2. Okay, given x1, x2, so there must be some c between x1 and x2, such that fx1 minus fx2 equal to the derivative at c times x minus 1. And this will tell us that if you take the absolute value on both sides, and since the derivative is always bounded by m, so you can see that this is it's controlled by m times x1 minus x2. And that's enough to see that f is uniformly continuous, as we can see from the previous homework. And this will always lead to what we call the Lipschitz continuity. And Lipschitz continuity will actually imply f is uniformly continuous. Okay, so this is the number 6, okay? And number 8 is very interesting. Number 8 say that now you have a kind of control like Lipschitz continuity, but however, it's stronger than that. So this means that for every x, y in R, and no, so I just give you a function without any assumption, okay? F is a function. And besides that, this function satisfies this estimate and nothing else. I didn't assign anything else. So what I'm having here is the assumption says that the difference of function value is always controlled by the square of the difference of the x minus y squared. And then here we want to prove that f is constant. Okay, we want to show that f is just a constant. Now this is a non-trivial result. Okay, it depends on a couple of things, right? So the idea is first we're going to so the idea is to look at the derivative. But however, the function does not carry any derivative. The function f is not assumed to be differentiable. So you cannot assume that f carries a derivative. But however, the estimate will tell us something. So it's from the estimate. So we're going to have that the ratio fy minus fx divided by y minus x, this ratio is now bounded by y minus x. So this is obviously true if you divide x minus y on both sides. Okay. Now, why this is useful? Because the left-hand side, you get a ratio. You get a ratio, okay? On the right side, you have y minus x. Now, let's let the x goes to x approach to y, okay? Let's see x approach to y. Now, if x approach to y, you get you can see the right side, you can see the limit y minus x goes to 0. So therefore, it's also implied that the limit on the right side also goes to 0, right? Because the left side controlled by right side, okay? So what does it mean? This simply means that derivative exists, not just exist, but also f prime x equal to 0. Okay. it's also equal 0. So from the assumption of this problem, initially we don't know whether f is differentiable, but however, this estimate guarantee that the derivative not only exists but always equals 0. Okay, and so that's enough to show that f is differentiable. Not just differentiable, the derivative is a 0 function. So this means that f is a constant. That's it. Okay. Now a variation of this problem is like this. Now here is a typo, some typo here. So here you can see there's no alpha on the left side. Okay. So suppose I assuming fy minus fx is controlled by x minus y to alpha's power. For any power alpha is greater than 1, then you are supposed to get the same result. Okay, you can think about it. Okay, and here in our in problem number 8, we're basically saying that when alpha equal to 2, this is true. Okay, but however, if alpha is any alpha which is greater than 1, so you'll get the same result. Okay, but however, if you choose alpha is smaller than 1 or less than 1, then you are not going to get anything like that. Okay, so it's a formula. Actually, it depends on the value of the alpha. Okay, so this is the homework problems. Okay, so now today I'm going to continue to cover the rest of the section in chapter 5. Okay, so last time we devoted ourselves to study the mean value theorem. So there's a sequence theorem. We go from the interior maximum theorem, then go to the Rolle's theorem, then mean value theorem, then Cauchy mean value theorem. So there's a sequence of theorems interrelated to each other. Okay. Now mean value theorem is a very powerful theorem. Okay, the mean value theorem can be applied to many situations to give a lot of a nice result. So that's something we are going to see today. Now, first things we're going to look at is we are going to prove a new theorem called the Darboux theorem. Now, what this theorem means, tell us. So here's the situation. Let's say that I have a function f, and I know that it's differentiable. Now, here when I say the function is differentiable, I just mean that the derivative of the function exists on the entire interval. I didn't mean anything about the continuity of the derivative or not. Otherwise, the function is called continuously differentiable. So here, what we are assuming is f is just differentiable over a and b, including the endpoint a and b. So let's say that on the left side, the derivative at a equal to capital A. On the right side, at the right endpoint, the derivative equal to capital B, assuming a is not equal to b. Okay, so this means that between a and b, there's many other values that are not equal to b. Now, this theorem says that if I choose a c between a and b, capital A and b, so this means I choose another value between a and b, then the conclusion is that there always exists a c and inside a and b, such that the derivative at this point is exactly equals to the value c. Okay. So this theorem is very significant. As we are going to talk about the consequence later, but and the first you can see that the derivative, once I know the derivative at endpoint, then any value in between cannot be missed. Okay, so you can always find points to achieve a different point. At the different point, the derivative will equal to any value between A and B. Okay. So let's look at the situation. Now here's a picture. Okay, you can see the picture here. You have a function, right, defined from A and B, and you can see that I draw some tangent line here. The tangent line at A and tangent line at B. So by the assumption, so they are giving the slope is given. Okay. At A, the slope equal to capital A. At B, slope equal to capital B. Now, in this picture, you can see that actually the A is greater than B. Okay. Now this theorem says that for any value c, okay, for any value c, you can always find some point in the interior so that the slope of tangent line at that point is actually equal to c. Okay, now if you look at this picture carefully, you can see that so this theorem simply says that the slope of tangent line, okay, is gradually vary from one side to the other. Maybe it's not going to be continuous, but however, it's not going to miss any value in between. So that's the result. Okay, so now let's see how we can prove this. Okay, so let's say that I have a value between A and B. Okay, then I'm going to search a point C between little a, little b, so that the slope at the C should equal to this capital value, the capital C. Okay, so here the trick is I define a new function called gx. Gx equal to our original function minus cx. Okay, C is the value are given, which I know that is between A and B. So cx is a very simple function. It's just a linear function. Okay, so therefore, for the g function is carry the same differentiability property as the little fx. Okay, then I can take the derivative at g prime. Then this means that g prime x should equal to f prime x minus c, because the derivative of cx is just the constant c. Okay, so that's our starting point. Now we have to divide it into two special cases. Okay, the case one. Now this case one and case two, actually they are parallel, similar. So, but however they are different. So case one means A is greater than B. It's just by the previous picture you can see A is greater than B. Slope on the left side is greater than the slope on the right side. Okay. Now if A is greater than B, then this will affect the G prime. So you think about G prime A at the left point. G prime A will become what? Will become F prime A minus C. Okay, now you can see that the G is greater than B, so C is between. So what does it mean? So G prime A should be what? G prime A should be what? It's greater than C, right? Because C is between A and B, and A is greater than B, so C must less than A. So therefore, the G prime A has to be greater than 0. And also, the G prime B should be less than 0, because the C has to be greater than, okay, the C has to be greater than the G prime B. Okay, so in the case one, when A is greater than B, then I'm going to have this situation. The new function, the derivative of new function at A is greater than 0, at B is less than 0. Okay. The case two is when A is less than B, and then you are going to get the, sorry, I have typo, I should switch the sign, okay? When I type this, I forgot to do that. But it's in the case two, they're basically the opposite case. In the opposite case, the case two somehow is similar to case one, okay? So I only want to look at the case one. So let's assume the case one. So G prime A is greater than 0, and G prime B is less than 0 in this case. Now, what does it mean? How does this help us? So this simply saying that at the point A, now G is increasing near A, because the derivative is greater than 0, so it means function at least is locally increasing. Okay. Now at endpoint B, I know that G prime B is less than 0, so this means that the function decreasing at B. Now you think about this situation. So the function starting from A begin with an increasing mode, and end the function end at the right endpoint, right? It's a decreasing. So you can see that this function must achieve the maximum value at some point C. Okay, must achieve. So this is actually follows the interior maximum theorem. Okay, so once I have a maximum point in the interior of A and B, assuming the maximum achieved at the point C, then the theorem 1.5.1 will imply that G prime C is equal to 0. Okay. Now G prime C equals 0 simply means that, so you look at what is G prime C. G prime C equal to F prime C minus C. So this implies that the F prime C must equal to capital C. So therefore, the C is achieved by some point inside interval A and B. Okay, so that's the proof. So this proof is actually not directly reduced to the mean value theorem. It's reduced to the basis of the mean value theorem. That's the interior maximum theorem. So that's called a Darboux theorem. Okay, so this is an important result. So if you view this picture again, you can understand why this is true, because the derivative, if you consider the G function carries very special properties. Okay. Now this theorem has a very important consequence. Okay, I'll summarize this here. So what is the consequence? Is saying that so once I have a function f is given, then the derivative of this function is different from the original function, right? The derivative function and itself may not be continuous, okay? Because at the beginning, I didn't assume anything about the continuity about the derivative. The derivative may not be continuous, but the derivative must take every intermediate value from A to B. So that's the conclusion we can make. Okay. Now, why this is important? Because this is a special property that every derivative function must satisfy it. So this means that the derivative function carries some special property. Not every function can be considered the derivative of another functions. Okay. So if a function does not satisfy this property, then this function cannot be the derivative of another function. Okay, so the derivative function is not a general function, it has to be some special function. At least the derivative function cannot miss any value from the left end to the right end points. Okay, so that's the critical result follows from this theorem. Okay. Okay. Any questions? So this is a Darboux theorem. Okay. The next thing, or the last thing we want to talk about is the now. Before we talk about last thing, we talk about homework number 5. Homework number 5 say I'm going to work this homework with you. Okay. And this homework says that I have a G function. Okay, with Gx equals 0 when x less than 0, and G equal to 1 when x greater than 0. So this means that on the left x-axis, the function Gx is identically equal to 0. And on the right axis, the function is identically equal to 1. So right at the point 0, the function carries a jump discontinuity certainly from 0 to 1. So you can see this function carries a jump discontinuity. Okay, it takes only two values, 0 and 1. So from here, we're going to see that there does not exist a function such that G prime equals Gx. So this is exactly precisely I said before. So this function does not satisfy that special property. It cannot be qualified as the derivative of certain function. Okay, this is directly follow the previous result. Because suppose there's a function f, so that f prime equals Gx. Okay. Then by the Darboux theorem, you can see that there must be so you can take another value between 0 to 1. For instance, take a 1/2. So the Darboux theorem says that there must be a value c so that f prime c equals 1/2. Okay, so this means that there must be a value c so that gc equals 1/2, but such a c does not exist because g function only takes two values, 0 and 1. So this saying that this saying that the g cannot be the derivative of another function. Okay, so that's the homework number 5. Now this homework can be varied in different ways. It's an important result. Okay, now the last thing we want to talk about is a complicated thing. So I'm trying to make things simpler. So this thing is called a Taylor theorem, and probably you actually from calculus theory, and you learn this result. Now this is just a Taylor theorem, so it's different from what we call the Taylor theory. Okay, it's different from Taylor theory. In calculus 1, you talk, I think in calculus 3. Oh no, in calculus 2 we talk about infinite theory. There's a section infinite theory, and they talk about the Taylor theory, spatial theory, right? If I'm given a function, sometimes I can expand this function into a Taylor theory. But however, in a function, in order for a function to be expandable to a Taylor theory, that function has to be an analytic function. It's a very strong condition, assumption on the function, okay? Now here, we're not talking about Taylor theory, okay? And we only talk about Taylor theorem. Now, Taylor theory actually is associated with the analytic function, but Taylor theorem actually apply to any differentiable function. We don't need to assume that the function is analytic, okay? Now, this is a complicated thing, so I'm trying to show you some simple case. Now, what is theorem? We first, let's understand this theorem. Now, the theorem says that I have a function, and the function is differentiable. Here, we're talking about high order derivative. So the derivative is also differentiable up to nth order derivative. They all exist in an interval AB, okay? Now you can see that the first, the function itself until the nth minus 1th order derivative, I have to assume they are to be continuous. Because assuming this is continuous is necessary because I'm assuming also the nth derivative exists, okay? Now in order for the nth derivative to exist, the n minus 1th derivative has to be continuous because if you have a function differentiable, that function has to be continuous. So nth derivative exists means that n minus 1th derivative is differentiable. So that thing has to be continuous. So that will actually tell us that all the previous derivative, they must also be continued. So this continuity is not assumption, okay? It's a necessary condition, okay? So basically we assume that I have a function and which carries nth derivative, okay? Now, so then I give us point C inside the interval AB. And then I take another point X, okay, another point X. What I want to do here is we're trying to express the function value at X in terms of the function value and the derivative value at C. So this is meanwhile something like this. I don't know fx, but I do know a lot of information at C. So from the information about C, I want to predict what the function is at X. But normally you can't do that unless the function is analytic, okay? But the Taylor theorem saying that, however, you can, to a certain extent, we still can do that with certain error, okay? So it's saying that there is a value gamma between C and X such that, okay, this is a complicated formula. Okay, so what it means is you can see on the left side, it's just fx. So fx is our target we want to compute. On the right side, okay, before the last term, okay, and they are basically the consists of information at C. Like the first term on the right side is fc, right? And the second term is f prime c times x minus c. Then the third term is the involves second derivative, and next involves third derivative until the nth minus 1 derivative. They all involve c, okay? But however, the last term is not just involving c, it's involved gamma between xc. Now the last term is considered as an error term, okay? So what I'm having here is a representation of fx in terms of fc and its derivative with certain error, which is given by the last term. So that's called a Taylor theorem. The basic thing about Taylor theorem is that the error term can be expressible by the nth derivative at the gamma for some point between A and B. Okay. Now this expression can be written in a sigma form. If you use a sigma form, I can write this in this way. So on the right side, you have a sigma. It's from the derivative from 0 to n minus 1. So the first part, so this consider the first part on the right side, is basically consists of all the information, available information at C. And the final term is the information, I mean, the error term involving the nth derivative at gamma. Okay. So that's the Taylor theorem. So I'm not going to just go ahead and prove the theorem in a general setting. And this is not going to help you. I'm trying to help you to understand the theorem, okay? So I'm looking at a couple important cases, okay? Now the first case it all depends on n, right? Now first, I'm assuming that n is equals to 1. Think about n equal 1, what happened? When n equal 1, you can see on the right side, there's only 2 terms, okay? The first term is fc itself. And the other term is the error term. It's just f prime gamma x minus c. So if you look at this formula at n equal 1, this formula is just like this. It's so simple, okay? And then, so this is being considered as a constant approximation. So basically, it's saying that I want to approximate fc or fx through fc with error, okay? So that's what we call constant approximation. Now we could let n equal to 2, and then you can see that on the right side there are 2 terms, there are 3 terms. So then you can see that so after the constant term, you carry the first derivative term f prime c times x minus 1. Okay, so the right side, the first 2 terms on the right side consists of what we call the linear approximation, because that 2 terms is a linear function of x. You're trying to approximate the fx using a linear function. Okay, linear function. And again, the third term is the error function. Now we choose n equals 3. Then you have additional term, right? So the right side, the first 3 terms on the right side, they are all consist of give you information at C. So this is considered as the quadratic approximation. Okay, so you can go on and on if you increase n value, so you get more and more. So basically, if you increase the next, if you think about n equal to 4, then you have the cubic approximation. Okay, so every time you have a higher order polynomial, so what we're doing here is I use a polynomial to approximate the function f with certain error. So all these approximate, you can see there's error term involved here. Yeah, error term. Okay. Okay. So this is the Taylor theorem. Now, if you look at the graph, let's look at Look at an example. Thinking about fx equal to ex. Okay, think about the exponential function and choose c equals 0, and then you can compute. You can see the constant approximation is just ex equal 1 plus the error. Okay, because e0 equal 1. Then the next linear approximation is just 1 plus x, because the derivative of ex at 0 is also equal 1. Then you have a quadratic approximation, because second derivative also equal 1. So if you expand everything out, so you can see the ex is equal to this sigma. So the expression is 1 over k factorial times xk. Okay, that's the polynomial. Okay, that's n minus 1 order polynomial. The error term is given by the last term. Okay, involve gamma. Now, graphically, you can see that, okay, I'm not going to show you the graph of the constant approximation. That's too simple. So you can see the red curve is ex, okay? Now here, the y equal to 1 plus x is the linear approximation. And this linear approximation, you can see that actually this linear approximation, the linear function representing the tangent line. So the linear approximation basically using the tangent line idea. Okay, so that's the best line fitting the function near the x equals to the c. And a quadratic approximation on the right side, you can see you are using a parabola, okay, at the same point to approximate our original functions. Okay, so if you go to higher order, you basically using higher order curve to approximate the function, original function. Okay. Now there are a lot of things we can talk about this. Okay, but we're not going to discuss this today in this class. But if you want to continue with 640, so the advanced calculus 2, and then there we're going to talk about infinite series. Then we're going to have a more discussion about this kind of approximation. Okay. Now we come to the proof, how we can prove this theorem. So I'm not going to give you a general proof. The general proof is written in the notes. You can look at this general proof, but instead I'm going to prove some two special cases in which you can clearly see the ideas. Okay, once you understand this special case, and you will understand the general proof. So the first case we want to try to prove is trying to prove the constant approximation. The constant approximation, why this is true, why there is a gamma to make this happen. Actually, you may see that this it's not difficult, because this is just the mean value theorem and nothing else. Because this equation can be rewritten as, if you divide by x minus c, you'll get fx minus fc divided by x minus c equals f prime. Gamma is between x, c. So this is just a mean value theorem, right? So the existence of gamma is guaranteed by the mean value theorem. Nothing to prove. It's trivial in this case. Okay, but the non-trivial case is when n equals to 2. It's this one, the linear approximation. Okay, and of course, once you understand this, and actually you can see how you can prove the quadratic approximation or any in the general case. And understanding this, the proof of this case is crucial for you to understand the general proof. Okay. Okay, so what we're trying to do is like this. I'm going to fix x and a c, okay? I'm going to fix it. So I know I choose a c, right? And I also have a value x. Now I'm going to free these two values, x and c. And then I will let the p, I choose p as a real number. It's just a real number, okay? I can always choose a p such that p is satisfied by the following relation. Okay, what is following? The relation like this. So the right side is basically fx minus fc minus f prime c times x minus c. So the right side is basically, if you look compared to the top formula, you can see that the right side is the fx, the left side minus the first two terms on the right side. So the resulting minus that, the result is subtraction should equals to, and which we want to prove is 1/2 f double prime gamma x minus c squared, right? But I don't know why this gamma exists. I don't know yet. But however, I can always say that, okay, the right side can be expressed somehow in this way. It's just equal to 1/2 times p x minus c squared. I can always say that because this p always exists, even though we don't know whether gamma exists. But I can always say that p exists because p can be expressed by the right side, fx minus fc minus f prime c times x minus c. The whole thing on the right side divide the 1/2 times x minus c squared, right? You get c. You'll immediately get a p. So such p always exists. Okay, now this is our starting point. I'm going to define a p in this way, by this relation. Okay, So now it's reduced to show what? So the only thing we want to show now is that we want to show that there is a gamma between x and c such that p is equal to the second derivative of gamma. If I can prove this, I'll prove the result. Okay, now how I can achieve this? How can I achieve this? Now cancel non-trivial part, very, very non-trivial part, okay? You'll be careful, very carefully in trying to look at the following steps. Now, I'm going to construct a new function, gx, defined on AB by the following. Okay, a gx, g function is called gy. Gy is basically equal to what? Equals to fx minus fy minus f prime y times x minus y, then minus 1/2 p x minus y squared. Now look at this expression. Now, do you know how this expression is related to what we want, to the previous formula? Can you see anything similar? They are very similar. Because that if you look at the previous, if you top formula, so this is what we want to prove, right? So you can see that the gx, okay, it's gy. Gy basically is the formula here on the top, okay, a minus on the left side minus the right side, and then I replace the c by y, okay. I'll replace c by y, and then I'm going to consider x is a fixed point, it's freezed, and looking at the function y, looking at everything vary in the y variable. Okay, except that the 1/2 derivative, 1/2 times, I mean the second derivative of gamma is replaced by p. So basically, it's the same side, replace the c by y. Now I'm trying to understand the behavior of this complicated function as c varies. So I choose c as a new variable. So I call this as y. Trying to understand this, okay? Okay, so why does this help us? So let's begin to examine some property of gy. Okay, obviously g is continuous and carries derivative in AB because f is twice differentiable. Okay, so you can, because everything involved in this formula only involve first derivative. If you're allowed to take another derivative. Okay. Now first you can see that gx equals 0. Now this is so clear because y, if you replace y by x, the right side will become fx minus fx, canceled. The third term is f prime x times x minus x, also canceled, equals 0. And the last thing also equals 0. So gx always equals 0. But not only this, but also from the assumption, from the definition of p, you can see that gc also equals 0. Because if you plot the y by c, okay, you can see the right side is just fx minus fc minus f prime c x minus c, then minus 1/2 x minus c squared. So this is precisely the things I used to define the p. Okay, a p is defined that way to make the right side equal 0. So therefore, so you can see that not only gx equals 0, but also gc equals 0. Okay. Now, if you have a function now, and at one endpoint, that's at x, okay, the function is equal 0, and on another point, the gc equals 0, and then you know that I can apply the Rolle's theorem, the Rolle's theorem we talked about last time. But the Rolle's theorem says that there is a gamma between x and c, okay, such that g prime gamma equals 0. So that's the key point. I connect this problem with the previous result, the Rolle's theorem or mean value theorem, okay? Now this will imply our final result, 1. Now we are in a position to compute the derivative of g, okay? Now, if you, okay, so I'll keep getting the typo here. On the right side, on the left side, it's supposed to be G prime. Okay, not the GY. It's supposed to be G prime. So if we take the derivative of G prime, I'll take the derivative of G function. On the right side, you can see that the first term will disappear because fx is a constant. X is supposed to be fixed. And the second term, taking derivative, you get the minus f prime y. And the third term is a product term. So you have using product rule. So your first part, you get f double prime y, x minus y. Then the second part, you differentiate in the y, okay, x minus y, y. So you will, the derivative of y equal 1, but it's carried a minus sign. So it's become f prime y. Now on the right side, on the fourth term, so okay, p is a constant. You take the derivative x minus y squared, okay, use power rule. So the 2 and cancel with 1/2. And the differentiating y carries another negative sign. So that's why you have p times x minus y. Okay, and now you can see in this expression, and there's two places involved f prime y with the opposite sign. So these two terms canceled. So therefore the resulting term is minus f double prime y times x minus y plus p x minus y. Okay, that's the derivative of g prime, gy. Then since gy equals 0, g gamma equals 0, g gamma equals 0 will obviously imply that the minus f double prime gamma times x minus gamma plus p times x minus gamma equals 0. And then you cancel x minus gamma. You will immediately get p equals to f double prime and gamma. So that's prove the result. That's prove our result. So that's the proof of Taylor theorem in the case of the linear approximation. Okay, and this proof is actually give you the general idea how to prove the general case. So in the general case, if you look at the notes, and you'll see that you construct the general function gy, and they do the same computation. You'll see the cancellation in the final step to get this result. All right. So I'm not going to repeating the written notes if you're interested. So you first understand this case, then you try to read the notes again to understand the general case. Any questions? Okay, so I also assigned 2 homework. So these 2 homework are also important. So I'm going to, so you should work on this homework and come back to this homework next time on Tuesday. And remember, we have 2 more classes, Tuesday and Thursday, and they're both classes I'm going to start at the 5 o'clock. I'm going to sending out the announcement of that. Right? Any questions? Oh, no questions. So the class is finished today. Thank you.